Hey everyone, and welcome back. Let's just jump right straight into today's explainer, because we are tackling one of the most complex, high-stakes challenges in modern tech, integrating AI into critical enterprise infrastructure. We're going to be digging into a newly developed white paper that breaks down the Solveforce AI Pragmatics Layer. Basically, it's a brilliant deep dive into how we can finally stop AI from just making wild guesses and actually get it to understand the real-world context of its actions.
But before we get into the weeds, let me ask you a question. Would you let an AI automatically restart your critical production servers? Like right now, completely autonomously, based on nothing but a statistical prediction? Yeah, if you just broke into a cold sweat, you are definitely not alone. The stakes of ungoverned IT automation are just astronomical. I mean, one wrong move and your entire network is down.
And honestly, this brings us right to the root of the problem. Legacy AI fundamentally lacks context. Traditional models are, at their core, just pattern-matching engines. They spit out a statistical confidence score, and they optimize local isolated components. But they don't actually understand the operational consequences or the intent behind a command. And without that deeper understanding, executing an infrastructure change isn't an intelligent action at all. It's literally just a highly mathematical, very dangerous guess. Okay, let's dive into this. We're going to walk through the Solveforce framework step by step. We'll cover the danger of ungoverned AI, move from signal to pragmatics, look at building the context graph, check out the digital Helmsman cycle, and finish up with the learning gate.
Starting with Section 1, the danger of ungoverned AI, why confidence isn't enough.
Notice the huge contrast here. On one hand, you've got legacy AI, which, like we said, just hands you a confidence score. It's basically saying, hey, I'm 95% sure this command means X. But Solveforce AI takes a completely different route. It produces a multi-dimensional calibration vector. In plain English, instead of optimizing one tiny little local piece of the puzzle, it coordinates the effects across the entire tech stack. So it isn't just asking, am I confident? It's asking, what does this actually mean for the whole system? And that crucial point is captured beautifully in this golden rule from the white paper. Confidence is never equivalent to correctness, semantic fitness, pragmatic fitness, safety, or authority. Look, just because an AI is 99% confident that a statistical pattern matches does not mean the command is safe to execute or that it even has the authority to do it. High confidence without context is pretty much a recipe for disaster. Which brings us to Section 2, from signal to pragmatics, the 5-pillar ascent. To see how they prevent those massive errors, we have to look at how Solveforce organizes digital infrastructure into these 5 pillars. It's kind of like a language. At the very bottom, step 1, you have the signal, so the actual physical state, like voltages or optical pulses. Step 2 is grammar, the connectivity and permitted rules. Step 3 is syntax, your network and cloud structures. Step 4 brings in semantics, identity, meaning, security. And finally, right at the top is Step 5, pragmatics. This is where AI actually lives in their architecture. It's where that meaning transforms into context and governed action. Now, don't let this massive architecture diagram overwhelm you. It's a really cool map of their unified intelligence architecture, but for our purposes today, we're just zooming in right at the top, on the pragmatics layer. That is the exact spot where all those signals and semantics from the lower layers bubble up and meaning finally becomes a safe, governed action. All right, Section 3, building the context graph, applying meaning and context. So, how exactly does this AI lock down a command before it breaks something? Well, it uses this 8-dimensional context graph. Before any consequential action happens, the AI has to verify every single one of these bullets: identity, the exact entity, network topology, time, the domain meaning, the intent, authority, and the final consequence. If you tell the system to restart the service, that command is locked. It literally cannot execute until all 8 of these dimensions are fully verified. Let's look at a classic IT nightmare to see why this is a total game changer. Imagine someone types a really vague command, block the agent. I mean, what does that even mean? Is it an AI agent, telemetry, a human? An admin would spot that vagueness instantly and ask for clarification, right? A legacy AI might just guess and accidentally nuke your critical endpoint security software. But the Solveforce system uses the context graph, realizes it's ambiguous, locks the action, and actually asks for clarification. Catastrophe avoided. Moving into Section 4, the digital Helmsman cycle, navigating operational reality. So once the context is perfectly understood, how does the system actually pull the trigger? The white paper uses this amazing analogy, the Kybernetes, or the digital helmsman. Instead of blindly issuing commands and just hoping for the best, the AI acts as a bounded control system. It steers the ship by sensing deviations, constantly comparing what your infrastructure is actually doing with what the policy says it should be doing, and then makes continuous, verified course corrections. And if an error does happen, the system doesn't just throw up its hands and log some generic failure. It decomposes the problem into these 7 specific error types. And this is so vital, guys. Treating all failures as one big generic error is a huge risk. Think about it. If a physical cable gets unplugged, that's a measurement or disturbance error. If the AI treats that like a generic failure, it might try to rewrite a whole network security policy just because a cord fell out. By breaking errors down into state, measurement, semantic, pragmatic, policy, execution, and disturbance, it routes the exact right fix to the exact right target. And all of this is run through what they call the 16-step recursive cycle. We're not going to read through all 16 steps right now, but the main takeaway is the sheer rigor of this process. It turns those abstract AI guesses into a strictly governed progression. A command goes from observation to simulation to strict authorization. It's only acted on within bounds, and then it is independently measured and verified. An action isn't truly finished until the cycle proves the actual real-world outcome.
And finally, Section 5, the learning gate, safe and verified evolution.
This is our final pillar. How does the system learn without corrupting its own core directives? If we look at this timeline for the learning gate, you'll see the AI doesn't just spontaneously rewrite its own rules the second something weird happens. An anomalous result just becomes a lesson candidate. From there, the system has to reconstruct the entire causal chain backward. It needs independent validation, maybe even from a human if it's high stakes. Only then does it become an approved learning object that can update the codex. Basically, learning requires a verified audit trail. And this perfectly highlights the foundational philosophy of the entire architecture, what they call the bidirectional coherence axiom. Everything sent forward must remain verifiable backward. An AI's action is only as good as the reverse path reconstructing its evidence. If you can't trace an outcome backward, through the execution, the authorization, the policy, the interpretation, all the way down to the original signal, then your system just isn't truly governed. Which leaves us with this final, provocative thought. Take a look at your own infrastructure, your own automated systems. If they can't explain exactly why they acted, if they can't reconstruct their evidence, and if they can't independently verify the outcome before learning from it, are they really safe? It's a fascinating question, and this white paper provides an absolutely brilliant blueprint for how we might finally build AI that actually understands the weight of its actions. Well, that is all the time we have for today's explainer. I really hope this helped demystify the pragmatics layer for you. Keep asking the hard questions about your tech stack, and we will see you next time.